Hello everyone, I am Sushmita from the Department of Electronics and Communication from Dr. Umayal Ramanathan College for Women. Now we are going to talk about the topic of open and closed loop configurations. Configurations of op-amp. Configuration of op-amp means the ways in which an op-amp is connected in circuit. Based on the connection, the op-amp can work in two different modes. First one is open loop mode, second one is closed loop mode. First one is open loop configuration of op-amp. This is the diagram of open loop configuration. The inverting terminal is connected to the input. The non-inverting terminal is connected to the ground. When no part of output is connected to input, it is known as open loop configuration. It means that there is absolutely no feedback present from output to input. The input signals V1 and V2 are applied to non-inverting and inverting terminal respectively. Differential input voltage VID is the difference between the voltages applied at non-inverting and inverting terminals. VID equal to V1 minus V2. The output voltage V0 equal to AV dot VID. Since V0 equal to AV into V1 minus V2. AV is the open loop gain of the op-amp. Ideally, open loop gain is infinite, but practically its value is very high. AV is very high. A small value of VID will drive the op-amp into positive or negative saturation, since V0 equal to plus or minus V saturation. Next, the closed loop configuration of op-amp. When a part of output is connected to input, it is called as closed loop configuration. It means that some kind of feedback is present in the circuit. Types of feedback. First one is positive feedback or regenerative feedback. Second one is negative feedback or degenerative feedback. Then briefly explain the types. First one is positive feedback. In positive feedback, the feedback signal and the original input signal are in phase with each. Here, the feedback is present between non-inverting terminal plus through the resistor RF. It is used in oscillators and skimmed triggers. Next one is negative feedback. If the feedback signal and the original input signal are 180° out of phase, then it is called as negative feedback. Here the feedback is present between output and inverting terminal through resistor RF. Negative feedback is used in almost every circuit using op-amp. For example, circuits like inverting op-amp, adder, subtractor and integrator use negative feedback. Following figure shows the negative feedback through a resistance RF. It is a closed loop configuration of op-amp. This is a diagram of negative feedback. The advantages of negative feedback: reduces the distortion, reduces and stabilizes the gain, increases the bandwidth, changes values of input and output resistance, reduces the effects of variations in temperature and supply voltage on the output of op-amp. Thank you. Hello everyone, I am Sushmita from the Department of Electronics and Communication from Dr. Umayal Ramanathan College for Women. Now we are going to talk about the topic of instrumentation amplifier. There are three operational amplifiers in the circuit of an instrumentation amplifier. The input of the differential amplifier is a non-inverting amplifier. For exact measurement of each input, data from transducer's circuit provides high input impedance. This is the diagram of instrumentation amplifier. The input stage of the inverting amplifier is formed by connecting two non-inverting amplifiers, represented as op-amp 1 and 2 in the above figure. The output stage of the instrumentation amplifier is the difference amplifier, which is the op-amp 3 is figure above. Next, The working of instrumentation amplifier. The output voltage Vout of the difference amplifier is actually the output stage of the instrumentation amplifier. This output voltage Vout is then the difference between the input signals applied at the input terminals. Let us consider V01 and V02, the output voltage of the two op-amps 1 and 2. Then the value of voltage Vout of difference amplifier is Vout equal to R3 divided by R2 into V01 minus V02. The value of voltages V01 and V02 is in terms of the input voltages and resistance. This is the diagram of input stage of the instrumentation amplifier. Consider the value of input voltage as V1 at node A. From the virtual ground concept, the value of the voltage at node B will be V1. At node G, the potential will also be equal to V1. Consider the value of input voltage as V2 at node D. From the virtual ground concept, the value of the voltage at node C will be V2. At node H, the potential will also be equal to V2. The value of current at input stage is 0 because we considered the ideal case. Therefore, the value of current remains same in all the resistors R1, R gain and R1. At node E and F, from Ohm's law, we can write I equal to V01 minus V02 divided by R1 plus R gain plus R1. Equation 1. I equal to V01 minus V02 divided by 2R1 plus R gain. As there is no input current at the input stage, hence value of current between node G and H will be, right? I equal to Vg minus Vh divided by R gain equal to V1 minus V2 divided by R gain. This is the equation 2. Equating both equations 1 and 2. V01 minus V02 divided 2R1 plus R gain equal to V1 minus V2 divided by R gain. The next step, V01 minus V02 equal to 2R1 plus R gain int V1 minus V2 divided by R gain. This is the equation of 3. The output of the difference amplifier is Vout equal to R3 divided by R2 into V01 minus V02. Therefore, V01 minus V02 equal to R2 divided by R3 into Vout. In equation 3, we substitute V01 minus V02. R2 divided by R3 Vout equal to 2R1 plus R gain into V1 minus V2 divided by R gain. Next step, Vout equal to R3 divided by R2 into 2R1 plus R gain divided by R gain into V1 minus V2. The output voltage of an instrumentation amplifier is in the above equation. The value of the overall gain of the amplifier is R3 divided by R2 into 2R1 plus R gain divided by R gain. Next, the advantages of instrumentation amplifier. Also, by varying the value of resistor R gain, the gain of 3 op-amp instrumentation amplifier circuit can be easily varied and controlled without changing the circuit structure. The value of gain of the amplifier depends upon the external resistor. Then by choosing the resistor value carefully, we can easily set the gain. As the non-inverting amplifiers form the input stage of the instrumentation amplifier, the value of input impedance of a non-inverting amplifier is very high. Thank you.
Hey all, I am Abhinaya here from Dr. Umayal Ramanathan College for Women and from Department of Electronics and Communications, and my slide is about linear integrated circuit. Phase locked loop PLL. Operations of basic PLL. It is a control system that generates an output signal whose phase is related to the phase of an input signal. It is in monolithic form. Basic principles: phase detector, low pass filter, error amplifier, voltage control accelerator VCO. Phase detector. It is basically a comparator. It works as an XOR gate. It compares the input frequency F in frequency input with feedback frequency F out frequency output. Low pass filter. It is used to remove high frequency component and noise from the output of the phase detector. It passes signal with a frequency lower than a selected cutoff frequency. For examples, haptics, electronics, etc. Voltage control accelerator. It generates frequency control by input voltage. Stages of PLC operations: free running stage, capture stage, phase locked stage. Free running stage. PLL works in the free running stage. The output frequency of this stage is dependent on the free running frequency of VCO. Capture stage. When input frequency is applied at the phase detector, then due to feedback mechanisms. Locked loop. Due to feedback mechanisms, the frequency comparison stores assonance. The output frequency become equal to the input frequency. This is the end of the video. Thank you so much to all who hear the videos with patience. Hey all, I am Abhinaya here from Dr. Romayal Ramanathan College for Women and from Department of Electronics and Communications. And my slide is about linear integrated circuit. This slide is analog to digital converted using voltage to time conversion. Analog signal can be converted into digital signal by counting the pulse from the variable's frequency source whose frequency is dependent on the analog input signal value. Counting is done for a fixed period of time. Analog to digital using time conversion. The block diagram shows the basic voltage to time conversion type of A to D converted. For this, analog voltage required to be converted to a proportional time period. Part for functional block diagram. The output of the comparator is at 1 as long as the output of the integrator V0 is less than VA. Part when the integrator voltage Vs is less than the analog voltage sample Vi as shown in output waveform graph. The comparator output is at positive saturations or a logic 1. Vs equal to VRD divided I power dou. Dou is equal to RC. Small t is equal to caps T. Vs equal to Vi. Therefore, T equal to dou Vi divided Vr. This is the end of the video. Thank you so much to all who hear the videos with patience.
Good morning to all. I am Deeva Lakshmi from the Department of Electronics and Communication, Dr. Umayal Ramanathan College for Women. I am here to explain about the IC723 General Purpose Regulator. Disadvantage of fixed voltage regulator: do not have the short circuit. Output voltage is not adjustable. This limitation can be overcome in IC723. Future of IC723: if offers modulable output for 3 volt to 37 volts. Thus ICs are used to make switching and linear regulator. It supplying 10 ampere output current with the help of an external pass transmitter. Thus ICs are used for different operations such as positive, negative, series, plotting and shunt. The block diagram of IC723. Simplified functional block diagram can be divided in 4 blocks. Reference generating block, error amplifier, series pass transistor, circuitry to limit the current. First, the reference generating block. The temperature converted Zener diode constant current source and voltage reference amplifier together from the reference generating block. The Zener diode is used to generate a fixed reference voltage internally. Constant current source will make the Zener diode to operate at a fixed point and it is applied to the non-inverting terminal of error amplifier. The unregulated input voltage plus or minus VCC is applied to the voltage reference amplifier as well as error amplifier. Second, the error amplifier. Error amplifier is a high gain differential amplifier with two inputs, inverting and non-inverting. The non-inverting terminal is connected to the internally generated difference voltage. The inverting terminal is connected to the full regulated output voltage. Third, series pass transistor. Q is the internal series pass transistor which is driven by the error amplifier. This transistor accurately acts as variable resistor and regulates the output voltage. The collector or transistor Q1 is connected to the unregulated power supply. The maximum collector voltage of Q1 is limited to 36 volts. The maximum current which can be supplied Q1 is 150 mA. Fourth, circuitry to limit the current. The internal transistor Q is used for current sensing and limiting Q2 is normally off transistor. If turns on when the IL exceed a predetermined limit. The pin diagram of IC 723. The topic is end. Thank you.